All right, so welcome back, and we're going to do some stuff on the open issues associated with VAEs. These are the things that people are currently working on, and they also highlight a few things that you have to consider when you're using VAEs as well. So these are the three main things that I'm going to cover. These are the things that pop up most frequently in the literature. Inference suboptimality and negative log likelihood trade-off. So this is the idea that our inference process is not learning all the information that we need to learn in the latent space. And we'll see how that can be sort of traded off against the log likelihood using the maximum likelihood estimation process, or the proxy for it. Then we talk about blurry images. People frequently say, oh, I can't use a VAE because they produce blurry images. I'd rather use a GAN, but we'll see that that's not necessarily the case, and we'll also see why we tend to get blurry images from the vanilla VAE. And then we'll finish off with disentanglement, talk about why that's important and how we measure or assess it. So we already mentioned that in terms of the log likelihood, we have various gaps that prevent us from estimating it closely and tightly. So the first one of them that we mentioned before was approximation gap, the idea we pick a variational distribution that is not sufficient to represent the true latent distribution. The second is the amortization gap, the fact that we're learning one set of parameter values over all of our data. And as I also mentioned, this isn't necessarily a problem because we can have a nice deep encoder and make sure our capacity is large enough to remove this gap. And finally, there's one thing that I haven't spoken about before, which is the parsimony gap. And this is how powerful is our decoder? Can we match our elbow to our log likelihood if we've got really powerful decoders? And what we'll come to see is that using maximum likelihood estimation isn't perfect because we're actually trying to learn two things at once. We're trying to reconstruct an image, but we're also trying to learn representations that are full of information. And so simply maximizing the log likelihood isn't necessarily going to achieve both. So in order to look at this, I'm going to talk about something called mutual information and a few sort of information theoretic terms. Mutual information is a really useful measure. The one that we're probably more familiar with is correlation. So both of these give us some kind of estimate for how related two distributions are. How much does knowing something about one distribution, how much does it tell us about another? So correlation is a first order statistical approach that we're probably familiar with, but it doesn't actually work in all scenarios. So if you have a straight line, we get a correlation of 1. The correlations are on the left in bold. Add a bit of noise, we get 0.8. If it's just random, or random normal, we get 0. If there's a negative skew, we get negative 0.8, and if there's a negative straight line, we get negative 1. So that's how we'd expect correlation to behave. But unfortunately, in these scenarios, where we can easily see that at least in these 4, there's a lot of dependence there, the correlation falls down. So here we've got a correlation of 0, even though we've got obviously that information in there. Here it's 0, here it's 0, and here it's 0. And as we'd expect, here is also 0. Now mutual information is, as I said, a way of estimating how much knowing about one distribution tells us about another. And so it gives us very similar results for the first, although they're all positive. But for the second, for this one we get 0.85, for this we get 0.78, 0.89, 0.85. So I would strongly encourage the consideration, at least, for incorporation of mutual information into your objective functions. Mutual information is actually quite challenging to compute, although there are more recent estimates, so estimation methods that can be used. And even if they're slightly noisy estimates, it doesn't mean that they can't actually help you learn. So don't be afraid of exploring mutual information. So we're going to take a bit of an information theoretic approach to KL divergence. Don't worry too much. I'm actually just going to look at this and then this. But the derivation is there. I actually went through this myself. It's a little bit tricky. There's lots of people that do this relationship, but they don't do the derivation. So it took me a little bit of time for this. So I wanted to put it on there because I was like, well, I can't chuck it away now. So if you take the slides, at least it's in there for you. So what we're going to look at is this prior regularization term that you should start to be getting familiar with. We derived it previously. So again, just as a reminder, since we've been eating sandwiches, I don't know what effect that has on your memory, but we'll have a go. So log likelihood here, reconstruction cost, mean squared error. Approach. But this term here is pushing what we learn towards the prior, which in a Gaussian case would be pushing information out, making it look more like a mean zero diagonal covariance Gaussian. So this penalizes us by removing information essentially, and we can prove that. It does actually have that other effect which allows us to move seamlessly and smoothly around the latent space. So it's sort of double-edged sword. But if you take an information theoretic approach and derive this into quantities like entropy and KL, you actually find that it equals this. So if I just take this term here, ignore the minus sign, if I just take this term here, then I get this. This is the result. It tells you that by making our variational distribution more like the prior, we are also penalizing the mutual information between our images X and our latent space Z, which is actually the opposite of what we want. Imagine the extreme case where we put this beta weight very, very high. We're essentially pushing all the information out of Z that's contained in X, which is literally the opposite of what we want to do if we want to achieve rich informative embeddings. So this term here is actually making our latent learning worse. It comes at that sort of double-edged sword again, because we're achieving this distribution, so we are able to move amongst it, but we are actually pushing information out. And that's, I guess, why it's called a regularizer at the end of the day. If it was putting more information there, it probably wouldn't be called a regularizer. So this is the proof, and it also has this term here, which is the inference marginal and your prior. But this term's not so relevant in terms of how much information is being stored. This is the key result. So we need to see if we can do some stuff to actually prevent this from happening.
So this blue one is the corresponding to the other blue one on the top?
Yeah.
Without the minus sign?
Without the minus sign, yeah. So if the KL, if I reduce this, then I'm also reducing this.
So maximizing expectation, so we have to reduce the beta. We have to reduce the KL divergence, and therefore what we reduce is what we have in blue.
Yeah. So if we put more pressure on this, and we make that contribution to the loss higher, then we're pushing more and more information out of the latent space by correspondingly reducing this because of the minus sign. Does that make sense?
Yeah.
Cool. So yeah, this is quite a useful derivation just to show categorically that we are actually removing mutual information between these two.
But some of this mutual information we want to remove because this may be nuisance factors and things like this.
Yeah.
So it's only some part of it that we don't want.
Yeah, and so that comes back to something else you said earlier, which is 20 dimensions would be enough for a face. If you're evaluating your network afterwards and seeing how many do I actually need to represent a face, it's actually kind of hard to interpret, because depending on what the weight is here, you've actually pushed out a lot of the small variance effects, including noise, but hopefully you're retaining the sort of a lot of variance. So this is a bit like PCA. By setting that to a high value, you're essentially removing more of your dimensions from your PCA. So think of this, if you're more familiar with PCA or probabilistic PCA, PPCA, think of this a bit like that. And I'm removing more dimensions by increasing that weight and removing more information about X. So yeah, you're right. Some of the information is actually not useful to us. So what does this look like in practice? This was from a master's a few months ago. So we put faces in. This is the head pose partition here. And you can see that whilst we've encoded head pose really nicely in these three dimensions here, this is the individuals looking left, center to left, this one's center to right, this one's up to down, sort of vertical head pose. These aren't being used at all. So these do actually represent traversals here, so I'm actually changing the value of that latent dimension, but it's actually having no effect. So this is an example of when either these aren't useful, or the beta pressure on the KL is too high to retain small variances in information. This is where also a qualitative evaluation is quite useful, because then I can look at it and say, well, actually, I only need these three dimensions to represent head pose. The fact that these aren't containing any useful information is actually not a problem to me. And you can either just use this partition of the latent space as is to predict head pose, or you could go in, look at it, and remove even more. So this is almost like doing a subjective form of compression. You can kind of identify and pull out the latents that are actually corresponding with something semantically meaningful. On the other hand, the expression partition, we get the same kind of thing. Most of the variance is encoded in these first few dimensions. There's a bit of appearance in there as well. So there's sort of like some kind of masculine or feminine kind of dimension going on here maybe, and then there's smile here, not smiling there, smiling here. But as we go across, you see there's less and less kind of effects as I traverse. So again, it's in both expression or appearance and head pose partitions. So what's the equivalent to this in GANs? It's sometimes called KL varnishing in VAEs. It's also called posterior collapse. They're collapsing to the prior. They just look like a mean zero diagonal covariance Gaussian. In GANs, we have something fairly similar. One author wanted to really distinguish between mode collapse and mode dropping, which are apparently two very distinct things. I didn't realize this when I read it initially. So mode collapse is when we have all of our data points, and then we collapse them to a single point in the representation, or this is in this case generated. So all these different points in the latent space correspond with one image. So that's like a mode collapse issue. If you imagine these are quite distinct points, but they're actually being now mapped to the same point in space. So you can relate that back to the injectivity, surjectivity, bijectivity things that we mentioned earlier on. Mode dropping, on the other hand, is actually just when you ignore them. So I think a lot of people say, oh, my GAN's experiencing mode collapse, when actually what they mean is I'm experiencing mode dropping. Because when you're not covering your modes, that's not the same as mode collapse. You're actually mode dropping, so you're getting a limited diversity in your generated space. I don't know how many people are using GANs, but I know they're quite popular, so I guess
it's very interesting because what we observe in GANs that they tend to not reconstruct certain things. So, for example, they will try not to reconstruct people.
Right, yeah,
so if you train them on images with people, the people will disappear.
Yeah.
And the reason, and it's precisely the mode dropping. And
Yeah.
that's because people are very difficult to fake. So rather than kind of risking being caught up with, say, false images, they'll simply say, it's difficult, I just skip it.
Yeah, yeah. And this comes back again to that two-sample comparison thing. It's an implicit density estimation method. We don't actually have a way of saying, is our GAN any good, until we have a way of sort of comparing it against the ground truth. And so again, measuring diversity in GANs is a big area of research. In VAEs, it's less of an issue because of the objectives that we tend to use. So we tend to get this zero avoiding behavior where we try and assign probability to all areas of the data space, even if it's not necessarily really well shaped and following the same form. So that would be a case of using an insufficient variational approximating distribution. So if you use a Gaussian, slap it on something that's very non-Gaussian, you might cover the distribution, but you're not necessarily going to recover realistic images, even though you're sort of covering the space. All good? So, this is one I mentioned. I'm not going to go through this. This is just one way to calculate mutual information. So if you want to start incorporating mutual information into your work, then this is one way to do it. Again, the advantage is you can decide what you want your network to learn. So if you have explicit information available and you want that information to be encoded in your latent space, you can specify it. You can call it in here, and then it will try and encourage that mutual information. Conversely, though, you could also remove it as well. So you could penalize your network for every time it encodes information that's specific to a certain thing that you want to remove. And that might sound, well, why would you want to move information? But it's quite important for things like debiasing. So if you want to make, say, your ML prediction invariant to, say, race, you could make sure that all of the information about race is removed from your embedding before you use it in your decision process, right? So this becomes quite useful and quite applicable in the sort of inverse case in sort of fair and unbiased machine learning. This is an example of what it does. So when you apply a GAN to this spiral distribution, you get a bit of a mush. Or alternatively to this distribution here, you get, again, a bit of a mush. If you apply, say, a mutual information regularizer on there or penalty, then you make sure that you're covering all of the data. Essentially what it's doing is it's saying, well, if my GAN's doing this, but it's not covering this part of the data, you penalize it and you say, this is a problem. We should be covering those data points. And so your density estimation becomes much more, covers more of your true distribution. All good? So I'm also going to talk about inference suboptimality, which again is how much information can we pack in a latent space? Why is it difficult to do that? I'm going to talk about it with respect to information bottleneck, which is actually quite a useful paradigm for all deep learning. It's essentially saying, well, let's say we're trying to get from X to Y. Y could be a label. In the VAE, it's actually X as well, so we could put X back here as well in the VAE, so we're trying to reconstruct the input. But say for a classifier, we might be trying to get our image X to predict a label dog or cat. So what information bottleneck basically describes it as is a way of squeezing information out of your network so that all that's left is what's important for that prediction. In classification, what you're actually trying to do is maximize the mutual information between these two. You don't actually care about the original image. You're trying to guarantee that's all that's left in this space. And this could be a layer in your network. Don't forget about latents for now. It could just be a deep layer just before your sort of softmax layer at your output. The information you want in that softmax layer is only actually the information relevant for your classification task. If it contains more information, you risk overfitting your training data. All right, so say that there was some domain or training data specific attributes that were in your training data that when you go to test, it's like, oh, this isn't working very well. But you think, well, surely it is because all the information is still in the label. But the trouble is, if you're also incorporating information that's specific to the training set, you're overfitting to it. So information bottleneck paradigm is a useful way to visualize your network and think, have I actually overspecified this network? Am I regularizing it enough that I push out the irrelevant information for predicting that label? So this is why things like dropout work so well, or L2 regularization, or whatever your favorite regularizer is in TensorFlow. There's also a way to relate this to sort of weights information complexity. So if you have tons and tons of weights, the complexity of them sort of increases exponentially, and then you can get all the information in there, but actually that's not necessarily helping you. So deeper is not better. I don't know if that's allowed to be said, but it's not always the case. So just be mindful of this paradigm and whether or not you're over-specifying your networks. Don't go sort of Rambo on it all the time necessarily. All right. So what we're going to do is now go back to VAEs and view VAEs through information bottleneck and see what's actually going on. We're going to look at two scenarios. We're going to look at limited decoders when our decoder for reconstructing the image isn't very good, and we're going to look at powerful decoders. All right, so this is also going to come back to what your goal is. Is your goal to just sample really nice looking images, a bit like how you'd use a GAN, or are you more about encoding useful information in that representation? And this is again why VAEs, they're so flexible. You can optimize them for whatever you really want to use them for. So first case, limited decoder. So imagine I've got a nice powerful encoder. That's all done. I've got my latent space, and now I'm decoding that to reconstruct the input image. If I have a low mutual information between the input image and the latent space, so there's not much information being encoded, that necessarily implies a poor reconstruction. So this is your conditional log likelihood. So this is your reconstructed image given your latent space. The reason why this is low is because your decoder is not very good, but also because the information wasn't in there to begin with. Right, so you've got a double-edged kind of effect here. You're removing information, but also your decoder is rubbish. But what if we have a high log likelihood? What if my images are actually still pretty good, despite the fact my decoder is not that good? All right, you might think, well, how can that happen? But achieving a high log likelihood, especially if you're using something like mean squared error, you might get blurry images, but they might contain all the information that you've put in the original image. So the reconstruction itself might look pretty good, even though they're a bit blurry, maybe not as good and sharp as you'd like. This actually implies that there must be high mutual information between your input and your latent space. Otherwise, how else could you recover the original image? Now the second scenario was if we have a really powerful decoder. Now if we have a really powerful decoder, this could be like using an autoregressive model. So quite a lot of these VAEs, if they're not interested in encoding useful information, they stick, say, an autoregressive model like Pixel CNN on the back. They just stick it on the decoder, and they use that because you get nice sharp images. Your conditional log likelihood actually becomes independent of your latent space. So P of x given z is equal to P of x. This just says there exists dimensions such that for all of your dimensions in your posterior, they're just equal to your prior. So this is saying that your prior dimensions are just, your latent dimensions are just your prior. There's no information in there about your image x. So again, powerful decoder, you actually make your decoder independent of everything that came before it. And this is why GANs work so well, right? They're just sampling from a noise space. It doesn't matter that there's no information a priori. They're just, well, how do I turn noise into something that looks like something from my real image data set? So you get nice images, but there's no concept of encoding or useful information there. And so if we look back at the variational lower bound, or the elbow, however you want to call it, this was the original elbow here. This can be rewritten as a fractional for KL divergence. Then you're basically replacing this conditional likelihood with just the likelihood of your data. So the problem with this is if you actually want to optimize this, just set this to 0. This is actually very easy for your network to do. It just says, oh yeah, okay, we're penalizing it because my latents look a bit like the prior. Well, that's not a problem actually. I'll just set them all to look like the prior. That way this term will disappear because I don't need it. All I need to do is reproduce the marginal likelihood, which is just, does the image look good? Does it have a low reconstruction cost? And so what the network does, say you have an image of, say, a dog and you've got a cat at the other end, you'll end up with this sort of optimized mush of cat versus dog. It won't necessarily, there's a little bit of a penalty on it to try and reconstruct the same as the input, but it doesn't have to. It just has to achieve a high log likelihood or high enough. So quite often when you have a powerful decoder, this sort of devolves into just a sort of auto-encoding behavior, and you don't actually encode anything useful in that latent space. Does that kind of make sense?
So how do we define powerful decoder?
That's hard. So I guess like they fall into two categories, at least through experience, which is that if they're autoaggressive, they work amazingly well. If they sort of by default give sharp resolution images, they tend to be too powerful for just sticking in this kind of architecture. That's kind of the best I can do.
Image reconstruction, subject.
Yeah. You could also measure it by log likelihood. So if your log likelihood suddenly has a shift in performance, like it's like, oh, maybe this is like too much. So there are various ways to guarantee that you actually retain information in your latent space. So when you apply your VAE yourself, how do you guarantee there's information there? There's basically mutual information penalties that you start applying yourself. There's various different options, like this one has total correlation, which is like a mutual information version of correlation. And there's other approaches there. You can look into the papers themselves. There's plenty of them. Like this is just a sample of them. This is, again, one of them, which put a mutual information penalty. This one used the penalty function method for optimization. So essentially here, this is the mutual information between x and z, and it applies this constant so that that term always has to be at a certain level when you're optimizing. And this is the effect. So the true distribution looks something like this multimodal sort of Gaussian. But if I put a penalty on it and I guarantee that there's mutual information there, I actually retain this shape. So this is the ideal scenario. It looked like that before. You have to trust me. It looks like this. You apply the network and it learns that density. However, if you don't encourage any mutual information, it can regress to the prior, which in this case is just a unimodal Gaussian. So this is a way to incorporate that mutual information into your objective function here. And it also shows that the solution with the highest log likelihood is not necessarily the best. So this comes back to something I mentioned before, where when you're evaluating these networks, you need to look at them from lots of different perspectives. You can't just say, what's my negative log likelihood? Is it better than the competition? It might be, but then you might have that. So again, you have to look at these things from different perspectives. So there are other ways to guarantee it. One way, which is quite popular, is to sort of tie this powerful decoder on after the main network. So this is the main VAE here. It produces some image and it looks something like this. So it brings in this leaf and it looks like this, or plant, and it looks a bit blurry. So this is what people often complain about with VAEs. They're like, oh, blurry images, so I can't use VAEs, but use GAN. But then if you actually tie a pixel CNN decoder on top of, so these aren't trained end to end, but you put them on top of this, then you can use that to sort of post hoc get your high quality image out. And this way you guarantee that, especially if this decoder is not very good, you get some useful information in here. That guarantees that you can reconstruct the image, not just sample a nice quality image, but actually reconstruct it. So in other words, information about the shape of this leaf, specifically this image, is encoded in here. It's badly reconstructed, but then I can sort out all of the local information, the local image information. All the global information is there. So this is actually still fundamentally the same leaf. All of the really important stuff is just the fine grain local detail that needs to be sort of filled out in this image.
Why can't that still be trained end to end then?
The trouble with end to end is that this image here just becomes part of the decoder. So this becomes one decoder at that point. So if you want to put pressure on this latent space, it has to be trying as hard as it can to produce the best image. But if this already deals with it for itself, it's just the same as having a powerful decoder on the end.
Just there is no information in the high resolution detail around various pixels. So this is reconstructed with pixel CNN decoder, which basically says how do I make it look realistic and sharp.
Yeah, because you could achieve a very low loss if you produced this, but it wouldn't necessarily have to look like the original image. So you achieve a nice low log likelihood, but there could be differences.
No, but you wouldn't just have the one loss, would you? Still, I mean, you probably have
an intermediate loss.
Yeah, mutual information on F in the latent space.
Mm-hmm. Perhaps, yeah.
And then
maybe
a construction loss on F in the original image.
So a way to sort of, if you could decouple these at least in terms of the loss, like end-to-end training-wise. There might be a way to do that. There's a paper, so do it. I don't know, maybe it's been done. Another way to do it is to introduce skip connections. This just increases the dependence of these later decoding layers on the latent space here. I haven't actually looked at the results in detail for this. I'm not 100% sure whether or not it could still just achieve what it needs to achieve without even utilizing this, even with the skip connections. So maybe that's worth exploring. And there are other ways to do it. So having hierarchies, just playing around these ideas to try and increase dependence on that latent space. There's people that incorporate sort of a PGM kind of a probabilistic graphical model perspective. This one's a really nice paper with structural VAE. It takes a very sort of probabilistic modeling approach. And then one of the more recent ones, actually VQVAE2, they use discrete variables, so they actually start quantizing in the latent space. This is actually the example I'll come back to at the end for some of the best reconstructions, and it actually guarantees also some useful information in the latent space as well. Joint VAE, another way. Again, we've been talking a lot about continuous variables. We're talking about Gaussian latent space, which is not discrete. So obviously some variables, latent variables, are definitely discrete. For instance, MNIST, like the class variable, obviously discrete. So we shouldn't necessarily be modeling that using a Gaussian. So there are ways to make these a bit more comprehensive for given your prior knowledge. So you can also play around with more powerful priors than Gaussians or more powerful approximate posteriors. So even the first work on VAEs by Kingma used autoregressive flow, I believe, and incorporated that into the model itself. So there are ways to sort of get around these limitations. There's also hyperparameter learning and sort of annealing for the KL versus the reconstruction term. So there's lots of different little tweaks that you can do. There's some example code if you've never optimized a Lagrangian. That was quite useful for me if you want to optimize over multiple parameters in your network. It's just a little snippet. And then there's this one. So anyone's familiar with compression? I imagine some of you here have probably dealt with compression before. Relating all these terms to all the terms that are commonly used in compression is actually a really nice way of having a look at what's going on here. And they also tie these terms up really nicely. So entropy, again, if you're familiar with this, you just recognize it as entropy. This is actually the same as the expectation over the marginal log likelihood, the negative marginal log likelihood. Your distortion, i.e. how bad is your compression when you reconstruct it, how bad is the reconstructed image, is actually the same as your conditional log likelihood. So that's the reconstructed distribution, the distribution of images that have been reconstructed from your latent space or your code, your latent code. And finally, rate, i.e. how much information am I able to transmit over that transmission line. In this case, the transmission line is that bottleneck in your VAE, is the rate, and that's equal to your KL between your variational distribution and your prior. So I think people have worked quite hard on sort of relating these mathematically. In some of these cases, the relationship is actually quite straightforward. But I think actually if you're really good at kind of tying all these mathematical concepts together, you can come up with new analogies between these terms, which should just be quite powerful. There's more and more work coming out every year, especially from the DeepMind team, sort of tying this stuff together. So the beta VAE objective is actually the elbow is equal to minus the distortion plus beta times the rate. So this is a direct analogy for compression. Literally right in the elbow in terms of how much you can compress information. Now if we have a look at how that plays out, the models become a trade-off between how much information I'm able to communicate through this channel, i.e. the bottleneck in my VAE, and how much distortion I achieve. So all models therefore fall somewhere in this grey area here. As I increase beta, I put more pressure on my network to look like KL. I'm therefore reducing the rate, how much information I'm able to communicate through my network. And I'm also increasing the distortion because I'm putting more pressure on the network to look like the prior. So I'm removing that information. Remember that mutual information bit in that KL term that we derived? So again, if we increase the beta coefficient, we're removing more of that mutual information between the input image and the prior, and we get more distortion. Moving the other way, we get more like autoencoding behavior. So here we don't penalize the network for looking like the prior. That's essentially widening the bottleneck. We're not penalizing it very much. It can do whatever it wants. In an autoencoder, you just do whatever you want, just get the input back. So that increases the rate because the channel capacity increases, and you can communicate all the information from start to finish, and then we end up somewhere down here. So low distortion, high information rate. Now, the one thing to note is that this perspective on its own on the left isn't enough for VAEs, because VAEs you can use for lots of different applications. So this might be enough for a compression task, because these are the two things you probably care about the most. But for VAEs, there's another task, which is that can I use that representation for something useful? So actually, where we end up here should be on another dimension. So these subsequent authors said that, well, we've got the rate and the distortion here, but we've also got some sort of subjective component here called usefulness, where it really depends on your priorities. If you don't care about reconstruction, i.e. if you don't care about being high up here, then you actually, as we've seen, put more pressure on the network to learn information in the latent space. So that might mean that we have a higher distortion, but it becomes more useful. So a less useful model might achieve better reconstruction, but if we don't care about that, then that's fine, it's not an issue. Well, okay. So here's an example of recent bit swap and bits back coding. These are the two recent papers, I think from Berkeley and Abil and Kingma. They compared it against all these compression algorithms and achieved some nice results. So this is just like catching on now. VAEs are starting to become quite an exciting topic in the field of compression.
It's Kingma's little brother.
Oh, is it? Got to be careful. I already had one incident with citation recently. So, okay, so we called inference suboptimality also KL varnishing. Oh, yeah, sorry.
In the last slide, you showed that there are places where the previous one
okay.
that we can have higher distortion, but still we can have more useful information in the latent space.
Mm-hmm.
And that is if we give more importance to the rate as compared to distortion, right?
Yeah.
But if when you were discussing it from a perspective of mutual information, it made sense. But why would forcing my latent distribution close to the prior, which could be anything, give me better representation in the latent space? How does it make intuitive sense?
Did you say why would pushing it to be like the prior encode more information?
Yeah.
It's actually the other way around. So if we push it more like the prior, we forget information. So yeah, in that sense, I think I see what you mean, because you're talking about, well, if we have high distortion, how can we end up with a high rate? And a rate is the thing we're trying to communicate. Maybe this is where the analogy differs, in the sense that we can define the latent space to be whatever size we want. So in with channel coding and like compression, obviously you're limited by whatever transmission line you have, and you set that limit. With VAEs, you can make the latent space huge. So simply by reducing this, making the distortion worse, for instance, will reduce the information in my image. But if I remove the penalty and I allow auto-encoding, I can fill up as much of that space as I want. So there's not the same limits as there is for compression with VAEs, because the fact that if it doesn't need the latents, it just sets them to 0. If it does need them, it starts filling them out and populating them sort of arbitrarily, and that would be like auto-encoding behavior.
But if I put mutual information penalty as well in my loss, can I do away with this term, the KL divergence between the prior and the
I think the problem with that is that you won't create a latent space that is traversable. You'll create a latent space that's richly packed in information, but again, it has more like an auto-encoding behavior. So you get all the information in there, which might actually be sufficient for your representation learning task. Say you want to use it for object detection. There's a risk that it will overfit on your data, on your training data, but that also you can't traverse it. So there's no like smooth distribution that's learned in that latent space, I think.
I don't think you could train it, because then you can't calculate the derivatives with respect to the parameters of the latent space. And this is essential to close the loop in training, at least the way we do it here.
So what if we remove the KL term entirely?
Yeah, because then you don't, then you have no constraint on the parametric distribution.
Yeah.
You have any distribution.
Yeah, and that would be like auto-encoding then, yeah. Oh, all right. So I guess the take-home message is that we're using log likelihood and maximum likelihood to try and optimize these networks. We're actually using a proxy for it, which is the lower bound on that, because we can't access it directly. But the whole sort of notion of doing this is slightly inefficient, because we're actually trying to maximize this joint distribution over both the images and the latent distribution, but we have no penalty on the latent distribution to actually learn anything with the sort of vanilla objective. So this is a case where, again, being aware of what your objectives are, what you're using, maximum likelihood in this case, we're using a proxy for it because we can't get quite where we need to. So we need to think, what are our pressures in order to actually retain information on our latent space, or can it just do whatever it wants? So I think there's a lesson, a sort of more broad lesson to be learned about sort of really understanding the objectives that you use in your networks. So the approach is unreliable, or it does work when the marginal imposes strong constraints on the joint. So this is basically saying, if my decoder is not very good, I have to encode useful information in the latent space because that's the best I can do. I have to get the information from somewhere. So there's a way to put a pressure on it with a less powerful decoder. However, in the high capacity regime, i.e. when the conditional likelihood is equal to the marginal, then the task of density estimation becomes disconnected from the goal of representation learning. And that's a bit like GANs. So you achieve, well, somewhat like GANs. Even with GANs, we don't achieve this, but we do a two-sample approximation to it and we get a nice looking image. We're definitely not doing representation learning, but there are obviously versions of GANs that do sort of try and achieve that. All right, so that's the end of the first problem with VAEs. Next one is always talked about as blurry images. So actually everyone seems to have a different view on why this is the case. When I look in the literature, someone says this is why it is. I'm like, oh, finally find out why. And then someone else comes out and says actually it's something else. I'm like, oh, good. So I don't know what the reason is. There's just like lots of different opinions on it. First one is the use of the L2 loss. You can derive the L2 loss from a Gaussian assumption and maximum likelihood. So L2 loss is actually only maximum likelihood because you're assuming Gaussianity of the output pixels. So L2 loss is sort of intrinsically tied to Gaussianity. So that's one argument, right? It's just L2 loss, it's calculating the mean, it assumes Gaussianity, we're going to get some kind of jitter around the pixel. If it's not quite right, we'll just calculate the average of it. That's why we don't get sharp images. Another one is VAEs learn latent variable representations that abstract away from low-level detail. So we talked about this before. All the global detail might be in that latent space, but the local detail isn't. So for instance, if you take a picture of my face, it's not going to get all of the sort of way my hair is falling, individual strands on my hair. In order to reconstruct that, you need a powerful decoder that actually infers what it's likely to be based on previous times it's tried to decode hair. You might want the hair to be encoded, in which case you need to like work harder to encode individual strands of hair in your latent space, and I guess that becomes again a problem for compression and reconstruction. So images don't have Gaussian structure. Okay, fair enough. If we're imposing a Gaussian on the latent space, surely we're actually just removing information, and we are. So arguably we're just sort of adding noise to it, and that's one of the sources of it. But one of the ones that comes back quite frequently as a reason for this, and I'm most kind of like convinced by this, because when we do have a powerful decoder and we're careful about what we do with a latent space, we do actually achieve really nice, sharp images. So there's no reason why we can't achieve them. I think most people have not like prioritized reconstruction for VAEs. And so the assumption has just been, oh, they're blurry. Better use a GAN. So the last thing is disentanglement. This is a real mouthful. I can't wait to read this out to you. A vector representation is called a disentangled representation with respect to a particular decomposition of a symmetry group into subgroups if it decomposes into independent subspaces where each subspace is affected by the action of a single subgroup and the actions of all other subgroups leave the subspace unaffected. So now you know what disentanglement is. That's all I'm going to say on it. Now, so I'll break this down a bit. Symmetry group, the first word that might be unfamiliar to you. If you've done physics, maybe not. So a symmetry group is basically an independent mode of variance. So if you were to think about an apple and I was to translate it or rotate it, those two are both symmetry groups. It doesn't matter where I translate it to, that's totally independent of the rotation of the apple. That's literally all it is. So it might be like, why don't I just say that? But they took a physics perspective on disentanglement, and it's quite useful. There's a lot of different definitions for disentanglement. The earlier ones were simply, are my latent dimensions independent of each other? Which is not sufficient because rotation is obviously three-dimensional most of the time, and color, RGB, LSV, we want these subspaces. We don't want independent dimensions, we want subspaces. So this is why they talk about subspaces and subgroups, and this independent thing, if I take an action, it doesn't affect the others. So that's the independence thing. Now disentanglement is important for a number of perspectives really. Like, first of all, if our model disentangles, it does more what we expect it to do, right? So if your latent space contains head pose independently of facial expression, that's what we want, that's what we expect a priori. If everything's entangled, it suggests that, say, like up and down is correlated with smile. It's like, that's not what we expect. We expect to be able to control head pose independent of facial expression. So if we achieve disentanglement, supposedly our models are more intelligent. Furthermore, we can use it to sort of separate partitions in our latent space. So this is again useful if you want to do debiasing and fair encodings. Let's say you've got a machine learning driven process like, does this person get a bank loan? If race or gender is in there, we might want to remove it. We can only remove it if we actually remove it. Not just we remove something that looks like it, but we remove everything that's correlated with it as well. Because there's no use just not... I saw a bank CEO recently saying, oh, our models are unbiased because we don't feed gender into the algorithm. It's like, what? What about all the information that's already correlated with data, with gender in that information? No idea. So if we achieve robust disentanglement, we are actually separating these out fundamentally so that they are no longer correlated with each other, not just correlated, no longer contain mutual information. So the ideal disentanglement is one with no mutual information and that they're independently controllable. It's what you would call interventional robustness. So if I make a change on purpose and I change, say like gender, if I change the gender, I want the rest of it to be completely invariant to that change. So that would be interventional robustness. I make an intervention and I don't see a change. So that's why it's important. It also actually increases predictive power. So you know, like I think a lot of people have probably come to the realization that if you train a sort of bog standard classifier, they're not that powerful. They extract features which are really useful, but the classification itself isn't great. So you might want to stick an SVM, for instance, on the back of that, or a random forest, or whatever it is. So you get better results, obviously, than just, say, sticking with a bog standard classifier, neural network, deep neural network. So getting disentanglement actually improves your predictive power. I think it just makes everything easier for your subsequent classification task. It also contributes some understanding to underlying generative structures. If we can interrogate it afterwards, we can see what's actually going on. And it might be obvious with an image of faces. You say, oh, well, obviously it's going to correspond with facial expression, blah, blah, blah. But what about if it's something more subtle? What if you've got data that doesn't look like something as intuitive as faces? So if I have a data set of demographics, for instance, how do I know what demographic is really doing what? And what latent variables exist under those demographics? Can I pull them out? And if I can I interpret them? And if I can interpret them, I can say, oh, that's interesting. It's to do with, say, like their salary, or it's to do with, I don't know, where they're born, or whatever it is. So this stuff has sort of wide-reaching implications and uses. And as I said, invariance and cleaning up images. So one of the things you mentioned about removing noise, that's also a task of disentanglement. You might actually be able to disentangle noise from the rest of it, and therefore sort of remove it from your latent space. That would clean up your images, essentially. Now, it's actually impossible. Okay, caveat that with it's impossible without supervision. So we're dealing with unsupervised tasks at the moment. Now, this is an example. F stands for female, Y for young, M for male, Y for young, O for old. This would be a disentangled representation. Disentangled in the sense that it corresponds with our prior knowledge about how these things should be disentangled. Young female, 0, 0. Old female, 0, 1. Young male, 1, 0. Old male, 1, 1. So this should be how you'd expect you'd code these yourself, right? In reality, we can achieve exactly the same statistical independence on the right. And this reminds me of Huffman coding. There are multiple unique solutions that will fulfill like a criterion, but they're not necessarily disentangled according to our prior expectations. So on the right here, these are all unique codes. That's great, but unfortunately, say, age here isn't working very well, and neither is gender or biological sex. So, yeah, this is actually what you often get out when you apply unsupervised methods. You put a penalty on them for independence, even with subgroups, and you achieve that statistical independence, but actually all you've guaranteed is sort of unique codes. They might not be traversable, they might not be sort of intuitive, and you might not be able to use them in the way you necessarily expect. So this is quite important. Say if you want to generate images and you want to tweak, say, how old someone looks in the image. I'll increase that. Oh, they've changed gender now. What's going on there? It's like, well, actually, it doesn't have to correspond with what we our prior expectation. So this is not sufficient in its own. The ability to sort of represent a joint as a product of marginals is not enough. So this kind of illustrates it. The ideal solution is here. If we have different types of car and we want different angles, you can see that if we pick this type of car, we can have a look at the different angles down this way, similarly across there. So that's a nice disentangled space. In reality, we either get what's called a shortcut problem, or we get this reference ambiguity where these concepts are kind of entangled. So if I go for a particular car and then I change the rotation or the view, I end up with a different car. And again, these can all actually fulfill the statistical requirements for independence. There's one more issue, which is to do with pretzels, apparently. So this is if you're using a variational approximation that just can't represent the shape of your true underlying generative factors. So I can't get holes in this to represent that. So again, be careful about what your variational approximation is and whether or not it's fulfilling the goal. This is known as manifold mismatch. Again, it's about choosing what variational approximation you use. There are various ways to measure disentanglement, but all of these are statistical. There's no other way of doing it if you want it objective. This one is my favorite, DCI metrics by Eastwood and Williams. They've been actually reviewed quite a few times in lots of different papers and been shown to sort of correlate well with all of them and also correlate the best, arguably, with our subjective expectations. I think the reason why I like it and the reason why it's done so well is because it splits it up into 3 different components. Informativeness, which is how much information is in my latent space. Is it powerful as a predictor? Completeness, which is a bit like if I predict the latent factors from my true ground truth factors, do they correspond individually? And disentanglement, which is as I've just sort of explained. So yeah, it gives you a 3-pronged attack to sort of evaluate your learning. And that's, as I said, really important for evaluating these networks because they can be a little bit mysterious. I'll basically go through these. Some of them include mutual information. A lot of them, all of these require ground truth factors, right? So you need access to the original factors. The idea is you have an unsupervised model, you train it on some synthetic data, you evaluate it using these because you have ground truth factors, then you deploy it into the world and you just cross your fingers. There's obviously qualitative assessment as well, so I've been through this example here. And then there's lots of different modifications to your objective function to encourage disentanglement. Again, can I enforce statistical independency between individual dimensions or subgroups? Unfortunately, they don't work. So we end up being stuck with some kind of supervision or incorporating adversarial training or training individual partitions of the latent space on specific data. All of these things require domain knowledge and access and control over the data. Here's an example with cycle consistency. This is actually quite limited in its supervision, actually. I'm not sure where the supervision comes from now, thinking about it. So here I have 2 images, and I'm partitioning the latent space for each of these images into 2 partitions. One of them is going to be appearance, one of them is going to be content. So appearance is supposed to be like, what actual animal is it? Content is more about what's the pose of the animal. So I can actually swap these over and then swap them back to make sure that after I've swapped them, they end up where they started. Now, if you haven't covered cycle consistency before, it might be a little bit like, what the hell's going on here? So I'm not going to go through cycle consistency in detail, but you can see that when I swap the content of this image to this, it stays a cat, but it changes its orientation. And the idea is that I want to end up back where I started, which guarantees that only certain information is encoded in certain parts of that latent space. And so, this is useful again if you want to create new images because you get nice fine-grained control of the individual partitions. But it's also useful if you want to just say, grab the content, use that as a predictor. And these are nice, compact, densely sort of informative representations. Another way is to use adversarial training. I like to avoid adversarial training if I can because, again, it's hard to train adversarial networks. In that min-max game, playing 2 players off against each other, one starts winning, the other one starts losing, and then you keep going backwards and forwards. It's hard to converge. The idea here is that supervision comes in the form of if I have sequences of a video and the same individual is in that video sequence, they're going to be the same for that whole sequence. So I know that regardless of which frames I pick from that video, they're all going to be of the same person. The thing that differs is their pose. They might be doing different things, but it's always the same person. So the network should be able to disentangle the identity of the person or the appearance of the person from their pose and their particular sort of what they're doing with their body. So the way we do this, we pick 2 images from the same sequence and we enforce a similarity. We say that whatever this learns, this should be similar for both those images. That's step 1. Second step, we pick 2 images, but we either pick these from the same sequence or from different sequences, and we get the adversarial learner to classify, are they from the same or different sequences? So if information about the person's ID is in here, this will easily be able to say, oh, yeah, they're different sequences, they're different people, done. But if you try and fool it, you have to remove all the information that allows it to identify the ID of the person. So by training this adversarial classifier, you remove this information from these partitions, combine them together, decode the image. So that's a way of incorporating adversariality. It can be very powerful, but it's hard to reconstruct, hard to replicate your findings, because I found actually a few papers which have been like, oh, we compared this against this other method, but we couldn't reproduce their findings. It was terrible. So again, I guess it's like if you go to your supervisor and you can't train your GAN, the supervisor says, try again, I guess. I don't know, like, these are challenging to train. This is full supervision. So if you really want absolute control over your network, you can go all out and you can actually generate your data yourself. So this was like for inverse graphics. So I had the author has control of the lighting, the pose, the expression of the face, and they can explicitly batch up images according to variance only in one dimension. So let's say I want to train a certain partition to say reflect the lighting in the image. I create a batch of images where the face is stationary, doesn't change, but the lighting changes. The network will only experience variance in that dimension, so it can only learn that dimension. We set all these other gradients to be the average gradient. They don't learn anything. And we only backpropagate as normal through that one partition that we're targeting. Then we move on to a different batch of images that vary in a different dimension, and we put the averaged gradients into the others as well. So the result is that you have nice, clean partitions for every single one of those generative factors that you already knew about. So this is full supervision. It's probably useful as a product, so you could productize this. You know, it's not necessarily good for sort of in the wild learning, AGI-esque learning, but it's good if you want to produce a product that's sort of maybe got quite solid results because you have full control. Here's another example of adversarial training. Here we have a label for a certain attribute. Maybe it's age. Let's just bin age into old or young. And the discriminator has to predict whether the image that they see is from an old person or a young person. This encoder has to try and fool that discriminator into not being able to classify old or young. And you can encode old or young explicitly as a label here and then combine it afterwards for your decoding or other purposes. All right, that's the end of disentanglement. We should have a break.